Hello, everyone. In our previous lecture, we have looked into how short reads can be generated. And these short reads can be paid end or single end. Paid end or single end. Paid or single. And we have also looked into how fragmentation is done to generate short reads. And we have discussed about three different methods. One that is mechanical shearing by using N2, and the other one is by RE enzymes, and the last one is by bead-based method. Today we'll look into how long reads can be generated. How long reads can be generated. Long reads, when you look at, can be generated by using two platforms. One is PacBio and the other one is ONT or Oxford Nanopore technology. PacBio generates around 15 kb to 25 kb fragments, whereas ONT, besides generating a fragment length of, a read length of 15 kb to 25 kb, can also generate 100 kb read lengths. And these reads that can be generated from ONT, they are called as ultra long, and these are nowadays popularly used to generate T to T assemblies, that is telomere to telomere assemblies. Now, having learned about short reads and long reads, right, and also the fragmentation in short reads, we'll now look at how fragmentation is done for long reads. And fragmentation of long reads, we obviously know that the fragments generated should be ideally bigger than 15 kb and 25 kb, and even equal to 100 kb or more than that. So for this fragmentation, there is a special equipment that is available in the market that is called as Megaraptor. And this Megaraptor generates fragment sizes from 5 kb to 100 kb. This generates 5 kb to 100 kb. And this is based on hydrodynamics. This is based on hydrodynamics. And here you have got a hydropore through which your DNA is passed through in solution form, and the speed through which the solution passes through decides the fragment length. Besides speed, one more metric that is important for fragment length here is your concentration of DNA in the solution. So these two metrics are said to be very important as far as the fragment length that is generated from your Megaraptor, that can be varying from 5 kb to around 15 kb. Now, having generated fragments from 5 kb to 15 kb, the next step is, like, you generally look into whether the fragments that are generated, both in the case of short reads and the long reads, whether the quality is good enough. Here, one thing that we'll have to keep in mind is the quality that you check here in the case of PacBio is immediately after the Megaraptor fragments are generated. Whereas here, once you generate the fragments, you purify your fragments, whatever method you use, attach your adapters, and then after attaching your adapters, you check the quality of the library. Because here in short reads, once you have your fragments on either sides, when you're attaching your adapters here, A1 and A2, right? This total after addition of your adapters is called as library now. So this library is now checked for quality in the case of your short reads, whereas in the case of your long reads, you immediately check the quality after fragmentation, and here the fragments directly go for quality check. The major difference here you have your fragments along with adapters that go in for quality check, And here, fragments directly going for quality check. Here, when you check for the quality in the case of short reads, the quality is generally checked by bioanalyzer, wherein you can check around 11 to 12 samples in one go. And the next equipment that can be used is tape station, which is high throughput version of bioanalyzer, wherein you can check around 96 samples in one go. Here, both these technologies are based on capillary gel electrophoresis. Both these technologies are based on capillary gel electrophoresis. So you know that capillary contains agarose, and your DNA is allowed to pass through the capillary, which contains agarose, along with the markers. Based on the position of the markers and your DNA, the fragment size is decided. Now, one thing that you'll have to know here is once you have this tape station gives you a graph like this. Now, what did I tell you? You have a fragment size. Let us say now you have a fragment size and you want to generate a 2 into 150 base pair fragment, 2 into 150 base pair read length. Sorry. For this, we decided in the previous lecture. Go back to my previous lecture and refer to find out what should be the ideal fragment length for generating 2 into 150. Now here, the minimum size that we would require is 300. And what did I tell you? It should be around 30 or 40 in excess to that. Plus, what did you add here? You added adapters on both the sides, right? So here, we add adapters on both the sides, and the adapter size varies from 60 to 75, depending on the kind of kit you are using for generating your reads. 60 to 70. So 60 to 70 and 60 to 75 on both the sides, it become 60 plus 60, that becomes around 120. So the total fragment size, if you're looking at, considering 300, 30, 60, and 60 will become around 450. And now, how does this look like, if at all, you want to find out whether you have ideally generated a library which contains a total length of around 450 base pairs or not? So this looks like this. Here on the x-axis, you'll be having your base pair length starting from 100 base pair. This will be around 200. This will be around 300. And this will be around 400. And this somewhere in the middle will be around 450. And this will be the concentration. Ideally, at the end of the tape station, if you see a graph like this, peaking at around 450, right? Peaking at around 450, and if this peak corresponds to 450, it means that the library size that you have generated is optimum for generating your reads of 2 into 150. That is how you actually find out whether the quality of the library that you have generated is optimum or not. Now, here now we'll go into the quality check for the fragments that you use for long read technology. Here in long read technology, what did I tell you? Like, you generate fragments of at least 5 to 15 kb. Now, the problem here with long reads is, and if you are again going in for, let us say, capillary gel electrophoresis, this capillary gel electrophoresis will not resolve your fragments beyond, let us say, 10 kb or 12 kb. What does that mean? Means even if the fragment is around 12 kb and your fragment is around 15 kb, they run to the same distance. So how does this gel run actually? Gel runs on the principle that it runs towards the positive charge and from the negative charge, because your DNA, having got phosphates that are negative, will move towards the positive. So normal capillary gel electrophoresis cannot be used for actually checking your quality, because these fragments cannot be resolved on a normal capillary gel. So what do you do now? What we do is we run a pulse field gel electrophoresis by placing electric fields. These red lines that I'm drawing are electric fields at the corners. And when you run a pulse field, this fragment that is there here now, instead of running in the straight direction, will move in a zigzag fashion. When it runs in a zigzag fashion, these fragments are now better resolved. And you'll have a better resolution of these fragments when you run a pulse field gel electrophoresis. So for checking the long read quality, right, there is a special equipment that is called as femtopulse. Femtopulse. So femtopulse basically runs on what technology? It runs on pulse field gel electrophoresis. Pulse field gel electrophoresis. Pulse field gel electrophoresis. So this is how you check the quality of your fragments. So we come to the end of checking the quality of the fragments.